Hey everyone. In 5.4b, we had ended talking about the second part of the fundamental theorem of calculus that relates the idea of the derivative to an integral. If we took the derivative with respect to x of the integral from some value, whatever, to x, please notice that was an x, of some f of t dt. Please notice that that variable is not x. We got f of x. This relates the idea of the derivative and the integral being inverses of each other. Now, we're going to go through some cases to make sure we understand this perfectly, because when we're taking derivatives, sometimes we have other rules we have to think about. So let's do the derivative with respect to x of the integral from a to some function g of x of f of t dt the long way. So taking a look at that, the integral of f of t dt, we'll use capital F to represent the antiderivative, from g of x to a, which we can rewrite as capital F of g of x minus f of a. And now, when we take the derivative of this thing, what happens over here, right here, we're going to need chain rule. It's capital F prime of g of x times g prime of x minus, and f of a, that's just a constant. And what's the derivative of a constant? 0. So, taking a look at what this simplifies to, the derivative with respect to x of some integral from a to g of x of f of t dt is little f again, of g of x times g prime of x. I'd like to add a little thing on the side here. What if you were to take the derivative with respect to x of some integral from some h of x to g of x of f of t dt? Because we have a bottom bound now, you have to be careful. It's not just 0 like it was up there. We would get f of g of x times g prime of x minus f of h of x times h prime of x. So let's look at a couple examples. Let's see if we can do this the short way without having to actually integrate plug-in functions and then take a derivative. So we have the derivative of the integral. We have a constant right there. We have a function cosine of 2x right there. Please note in our earlier definition right here, that f, that's the same, because when we integrate it and have the antiderivative, we're going to take the derivative and bring it back down to the original function. But now inside of that function, we have to plug in that top bound. So we're going to start with this idea of 3 times, not t, but some input, minus 5. What's going to go into that input? That top bound. Did I leave myself enough space? Just barely. Cosine of 2x. Now, what do we have to remember, though? That's all of that part right there. We need to remember our g prime, our chain rule. So we have to multiply this by the derivative of cosine of 2x, which is negative 2 sine of 2x. So this right here is f of g of x, and this right here is our g prime. Thinking about that cosine of 2x right there, that's our g of x, and there's our f of truly t right there. Okay, let's try it again. Thing to note, constant on the bottom, we like that. So, derivative of the integral from 3 to x of e to the t squared dt. So we're going to take our function e to the t squared. We're going to plug in our function, that's our top bound, there's our x. And if we're thinking chain rule, what is the derivative of x? Well, that's just 1. So you might have recognized this wasn't one of our new cases that requires chain rule, but if you thought about it, it's still fine. So the derivative of the integral from 3 to x of e to the t squared dt is just e to the x squared. At this point, if you're feeling comfortable and want to try this yourself, please do pause this, try the 2 at the bottom. If not, continue watching, see if something I say and do helps you understand this a little bit better. So now let's take the derivative of the integral from 2x to 9x of sine of t squared. So the derivative and the integral, essentially, they undo each other. We're going to have sine of something squared. What are we going to plug in, though? Our top bound, 9x squared. Because that's not just x, we need to remember chain rule. What is the derivative of 9x? That's just 9. And in this case, we have a bottom bound that's not a constant. Please don't forget, if we were doing this, remember it's f of b minus f of a. So we're going to do minus sine of something squared. What is that something we're plugging in this time? The bottom bound, 2x. And we can't forget chain rule. We got to multiply by the derivative of 2x, which is 2. So we could rewrite that as 9 sine of 81x squared minus 2 sine of 4x squared. One more at the bottom of this page and one more at the top of the next page before we get to something that maybe looks at least a little different, but maybe really isn't all that different. Derivative of the integral from negative 1 to x squared of 3t minus 4. Again, should try this out, see if you get it. Pause it, see what you get. I'm going to write my answer. 3 input x squared minus 4. We got to multiply that by the derivative of that top bound, which is 2x. Our bottom bound is a constant, so the derivative of us plugging in a constant into that antiderivative will be 0. And if you wanted to rewrite this, you could. We could write this as 6x cubed minus 8x. All right, one more at the top of the next page. Please note this time that we have the function, not the constant, as the bottom bound. You have 2 ways to do this. You can either initially think about this as rewriting the integral from one of our integral rules. When you reverse the bounds, you can just take the opposite value of the integral. You could do it that way, if you want to think about it that way. Or you can just remember that if we're plugging in the bottom bound, that's going to be after the minus. So we need a minus e to the power 2 times cosine 3x plus 1 times the derivative of cosine of 3x, the derivative of the bottom bound, not this function, but the bottom bound. The derivative of cosine of 3x is negative 3 sine of 3x. We want to clean this up. The only guess easy way, one way to clean this up would be get rid of the negatives, so we could do 3 sine 3x times the quantity e to the 2 cosine 3x plus 1. That makes it look a little nicer. No more negatives. Okay, I got one more problem, then I'm going to do a second half of the video for the particle motion problem. So find f prime of 2 if capital F of x equals integral 2 to 3x of 2t minus t squared dt. If we're finding f prime of 2, how about we first start with this idea that I want f prime of x, which is the derivative of the integral 2 to 3x of 2t minus t squared dt. We're going to use that second part of the fundamental theorem of calculus to get the value 2 times 3t minus 3t squared, all of that times the derivative of that top bound function 3t. The derivative of 3t is 3. If we simplify that, that would be 6t times 3, which is 18. Oh, folks, look at me going right here. Shouldn't have been writing t's. It's my fault. These should be x's. What am I doing? So it's 3x, 3x. So this should be 18x, and then minus 27x squared. Please note here that the 3 is getting squared. So it's 3x squared. Let's write that better so you can actually read it. That is 3x squared And 3x squared is 9x squared times 3 is 27. X squared. Okay, so hopefully this helps with using the second part of the fundamental theorem of calculus that requires chain rule when taking the derivative. In the second video, we'll go over the particle motion problem.